Hello, everybody. Good morning, good afternoon, good evening, and thank you for joining. Hi, Dan. How's it going? How are you doing? You're muted. Let me see if I can help.
Yep, there we go. I was muted just before. Sorry about that. How are you doing?
Good, good. I'm good. I'm excited. So this is already the last of our Road to Nodes workshops. So we had this is number 5. So we had 4 previous workshops. So it's been a journey. So we started with something very intro, very low key, and for everybody, and we worked our way upwards, I would say, towards data loading pipelines with Apache Hop, and last week we had Apache Arrow, Graph Data Science. And today we have Graph EDA using the Neo4j GDS client. So as the final episode of Road to Nodes. So I'm super excited about this. Before we dive in, and a couple of people who might be joining, since the beginning, or maybe for a couple of these episodes, and I hope you found them all very valuable to you. Probably know this. So Nodes is coming up. Obviously, this is why it's called Road to Nodes. And it's on the 16th and 17th of November. So in 2 weeks' time, more or less exactly in 2 weeks' time, actually. So if you haven't registered, and you won't have registered automatically if you registered for any of these workshops, please go to the website. I posted it in chat as well. I'll post it again in a second. It's going to be a fun event, and the main focus about this one is going to be that it's going to be a 24-hour live stream. So that means no matter where you are, and I see right now in chat, I see people from Ecuador, from Phoenix, Arizona, from India, from Canada, Ottawa, from Oregon, from Minnesota, Berlin, Germany, Denmark, Seattle, Costa Rica, Mexico. So no matter where you are, there will be something in your daytime. So that means you don't have to go crazy late or crazy early and watch the sessions. It's going to be in your daytime, and you can join and watch and interact and discuss things with the network, with the other people joining, all the graphistas that will be there. So I think it's going to be great, and I just to sum it up, please register, please join, and yeah, that's what I had to say about Nodes. Before handing it over to Dan, I'd like to make the housekeeping rules, I guess. So please, chat is open. So we have my dear colleagues Michael and Jason in chat. They will help out with questions. There's a Q&A panel on the right-hand side if you watch this on Big Marker, which you can use for questions. It's probably a little bit easier to track questions there instead of in chat. So because then messages can scroll by. So if you have a question, anything, please use this in the Q&A section, and then you type in your questions, and we can answer you there, or Jason and Michael will help with questions. So that's the main point. Point number 2 is obviously, yes, this will be recorded. You will share the video link with you all afterwards, so you don't worry if you have to drop out earlier. If you missed something, you can rewatch at any time. And also the slides that Dan is using, or is presenting has prepared rather, we will share them as well. So you get an email afterwards with these important points. I will share a link. Dan has kindly set up a GitHub repository with all the information there. I will share that also later with you, so you don't have to type anything straight or long URLs from presentations. We will post this in chat, so you have it ready for you in a second. Yeah, I think that's what I had to say. So I'm definitely looking forward to this. I can already slide over to your screen, Dan, so it's visible here. And yeah, I think we're ready to go. Enjoy, everybody. I hope you will have an interesting session. Thank you, Dan, again for presenting today, and for taking the time to present and to prepare the workshop. And yeah, with that, over to you.
Great. Thank you very much, Alexander. I'm And I will just add another vote for nodes. I'm looking forward to the event as well. So definitely encourage everyone to register. I certainly plan to be there. It's going to be a great event. But as you mentioned, this is the last Road to Nodes presentation or workshop. Really excited to be here. And we're going to be talking about exploratory data analysis and how it relates to graph. Before we jump into that, I'll just start with a little bit about myself. I'm here based in the United States. And I
Dan,
actually
sorry to
started my
interrupt
career as an
already.
accountant.
Do you mind going on full screen here while
Oh,
you're in the
sure.
presentation? I think that would make it.
Let me see if I
easier.
can. I will just jump over to the slides.
Yeah.
Here you go. Is that better?
Yes, much better. Thank you.
All right, sure. Sure. So a little bit about myself. I didn't start my career in technology or data science. My background is in finance and accounting, and I spent the start of my career working in the public sector as a forensic accountant and financial intelligence analyst, which is where I started to learn about networks and graphs more by building them from hand rather than the data science-based graphs we'll be talking about today. Spent some time after working in the public sector, went to one of the big accounting firms and a travel company where I was doing anti-money laundering and fraud investigations. And this is where I really learned more about the power and impact of data science and decided to move my career into that direction. Went back to graduate school part-time at Northwestern, which is in the United States. And I've spent the last couple of years working as a security engineer and a threat intelligence analyst at several tech companies, from startups to some of the biggest companies in the world. And joined Neo4j earlier this year, and been absolutely thrilled to be part of this company. With my background in anti-money laundering, I learned about them when the Panama Papers was published, and it's been a company that's been on my radar and that I've been a big supporter of ever since then. And so we'll talk a little bit about the agenda first. I'm going to start with a background and a conceptual foundation of exploratory data analysis. This is just to make sure that everyone's on the same page and we all kind of have a common understanding of the terms and approach and workflow that we'll be discussing. From there, I'm going to move to some notebook-based demonstrations. And there's 3 notebooks published in the GitHub along with these slides. I know they're putting the link in the chat, but we'll have one that'll be going through kind of traditional tabular EDA that many of us learn when we're getting started in data science. Then we're actually going to go through graph data modeling and a brief notebook for graph data loading, because this is very much dependent upon and connected to our exploratory data analysis. And then finally, we'll focus on some graph-based EDA where we'll use the GDS driver in Python, as well as the Neo4j browser and Bloom. And again, all of these notebooks are already published and completely executed on GitHub. I encourage you to follow along here, or if you want to bring up the notebooks in GitHub, that's absolutely a great option as well. One thing though, during this presentation, even though we're going to be using, there's a lot of code in these notebooks, a lot of technical concepts that we'll be covering, the big picture and the big takeaway will actually be a little bit more conceptual. And what I hope to emphasize is, how you think about your overall data science workflow or your graph data science workflow, how you approach data before loading it into Neo4j, and then after you have the data in Neo4j. It's a different approach than what many of us were traditionally taught, as we were learning data analysis and data science. And so with that, why don't we just jump right in. Also, if there's any questions, as Alexander mentioned before, please add them to the chat. This is a very full workshop. I will try to address questions if they come up, but I want to be respectful of everyone's time as well. And so if we're not able to answer questions during the presentation today, I'll work with the team and make sure we can address them in the Discord or elsewhere after the workshop. Again, I won't be executing much code live here, but if you have any questions either afterwards or if you're watching this at a future date, please feel free to reach out and we will do our best to get answers to those questions. And so why are we here? Why pick a workshop or why do a workshop on exploratory data analysis? As I mentioned before, I transitioned my career into data science, not from the start, but several years into my career. And many people, whether you're learning data analysis, data science in school or on a Coursera class or on Kaggle or Data Camp, we've all seen some very common data sets. These are easy toy data sets, the Iris data set, housing prices, Kaggle's Titanic data set, the Abalone data set, and I could have added 10 more to this slide. What these all have in common is that they're very accessible, easy to work with data sets to teach basic data science concepts. What they also have in common is that they're all tabular. And coming from an accounting background, I had been working with spreadsheets for a decade. This was a good frame of reference or a good entry point into data science, because at the same time, I know I was learning how to do Hello World in Python while trying to learn some basic data science concepts. But as we also know, not all data is tabular. I mean, that's why we're here. But as technology improves and as compute and storage and how we collect and process data improves, we're going to be working with more and more different types of data sets. We have image data, audio data, we have AlphaFold and reinforcement learning, semi-structured text data, and what we're here to talk about today, graph data. And we need to make sure that we leverage, a lot of us learned with tabular data, but those methods, sometimes they apply to different forms of data, but not always. And so what we need to make sure we're doing is adapting our approaches to the data that we're working with. And if there's only one takeaway from this webinar or from this workshop, it's that we need to adapt how we work to the data that we're working with. And that doesn't mean throw out concepts that we learned on tabular data. That I love, I spent a lot of time with the Titanic data set and some of these other data sets. They are great tools to teach concepts for data science and data analysis. And what we need to do is build upon what works. And we'll get into this a little bit more, but focusing on the business question, making sure that we have enough data, that it's complete, we have the right features. Are there any data quality issues that we need to address? Are there any, are we visualizing our data and exploring it from different perspectives? And then going through standard pre-processing and feature engineering steps to make sure that our data is ready for whatever the use case is. And doing all of this, leveraging some of the best common tools and libraries available, whether they're GUI-based applications or Python libraries, R, SQL, whatever your toolkit is, leveraging these techniques and tools to build upon what we know works. At the same time, we also need to adapt. In this case, we're going to be focusing on graph, but this concept could apply to audio or any other type of data that you might be working with. Is our problem a graph-shaped problem? Do we have a deep understanding of our data to develop a well-informed graph data model? Are we doing any pre-processing and feature engineering to get ready for graph? Instead of thinking in rows and columns, are we thinking in nodes and relationships? Are we visualizing graph patterns and developing graph-based features for our data? Learning information about the data that's unique to the graph form that we might not have accessible when it's in tabular or some other structured format. And so we'll revisit this slide near the end of the workshop, but these are some of the key points I hope you take away. And as we're going through the demonstrations, think about what is your process for working with data when you receive it, whether it's coming from a table in a relational database or a CSV or some JSON format. How are you analyzing that data and preparing to convert it to graph format when you're using Neo4j? And so building upon that, I want to take a few minutes and just review EDA, Exploratory Data Analysis. And to do that, I'm going to go back to a framework that many of us, I'm sure, are familiar with, the CRISP-DM model. if you learn data science in almost any platform, you probably came across this concept. And what it is, it's a general approach or a general cyclical workflow for how to approach a data science task. And it's a good common frame of reference that many of us working in data science can all relate to, even if we don't follow it exactly. But it does a really good job of showing what a workflow could be, or a concept to base your overall workflow on. And what I'm hoping to share here is that, with some adjustments, this can apply to a situation where we're actually working with different forms of data or transitioning data from one format into another. And you'll see here that I've actually added a couple of arrows because I want to emphasize how iterative or cyclical this actually can be when we're changing data from tabular to graph format, and how exploratory data analysis is really a key component of this overall workflow. And so we're just going to cover a couple of the topics at a high level, and then we'll jump into the actual demonstrations. So starting with the business understanding, this cannot emphasize enough how important this is, both for any data science workflow, but especially when you're working with graph data. And some of the questions that when we're working with our customers, trying to make sure that they're successful with Neo4j, we want to make sure, is your problem a graph-shaped problem? Is it something that's going to focus on relationships, whether identifying relationships or specific patterns of relationships? And that's important when you're working with the general database, but when you're focusing on a graph data science application, how is graph going to fit into an overall data science workflow? Most of our customers have established platforms, tooling, and machine learning pipelines. Is graph data science or graph data going to stand alone? Or is it going to be complementing something that's already in production? You might already have a tool or a pipeline that's in place, and you're leveraging graph data science to, say, generate node embeddings and feed those to an existing model or an existing pipeline. There's no right or wrong here. It's how does graph fit into your problem and your situation? And that's an important question to ask up front, because that will really drive the entire use case and how you build your graph data science pipeline. From there, we'll move to data understanding. And this is the core, this is the core of EDA. When you see data understanding, you're thinking about, what do I need to know about my data before I move to other analysis, preprocessing, modeling, and the other steps. And one of the other points that I'm hoping to I hope that you can take away from this workshop is, when you're changing the nature of the data, in this case, moving from, say, tabular to graph data, you actually need to perform data understanding, or EDA, multiple times. First on the data as is, to understand, okay, how is, if I'm getting my data from a relational database table, or building it out of a couple of joins, what is in my data right now as is? This is critically important because it will inform your graph data model. And it's not just the, say, the features or the columns in the data, it's also the content. If you have a feature with, say, 5 or 10 different labels, do you actually understand what all of those labels are in the data? I've worked in a lot of companies, large and small, and getting a good data dictionary isn't always easy, but it's a very, very important step of the data science process, even if it isn't necessarily technical. Having this understanding will also help inform whatever pre-processing you might actually need to do. Are you going to, that's a little bit more in the next step, but do you need to clean up the data, or remove some errors, or scale the data? Having a good understanding of the data as is will identify what steps you need to take to prepare it for data modeling and graph. But once you have the data in Neo4j, do you understand the data as a graph? You might not have brought in all the features. You might have changed or created features. And there will be aspects of the data that are unique to being in the graph format. And so in addition to validating your graph data model, do you understand the nature of the data as it is a graph? Because it's, in a lot of ways, totally different than how you might have originally received the data. And so performing EDA multiple times is I would say, necessary when you're changing the format of the data. Data preparation closely tied into EDA. These are some of the feature engineering steps that I mentioned before. You need to prepare the data to move it into the database, and then once it's in the graph database, are there other graph-specific features you might want to create? And we'll go through this a little bit more as we get into the demo, but there'll be features you create when it's in tabular form, and potentially features that you add or create when you move it into graph. And there's some cases you're creating new features that you probably could have done when it was tabular, but you'll see it's actually easier or a little bit more straightforward when you have the data as a graph. And so again, this is going to be an iterative, cyclical process that you'll repeat as you're working with the different types of data. Typically, modeling is the goal of this. It's preparing all the data and then feeding it into a machine learning model. But modeling is also important, or can be an important part of the exploratory data analysis process. Something I like to do with a lot of data sets I'm working with is to run a random forest model. One, because it serves as just a nice baseline when we're in tabular format. Before I've done some more advanced pre-processing or generated some features in the graph side of things, just run a basic model as is to see where are we kind of out of the box. But the other feature I like about this is you can, whether you're using scikit-learn or another library, you can figure out, okay, what features were the most important to the model? Which ones gave us the most information? And that'll help you also identify feature importance, which could inform what goes into your graph data model, what goes into the graph database, and then what additional analysis you might do to either boost up features you couldn't use or double down on the ones that you think are the most important. And so, modeling both in the tabular format and then with some of the GDS algorithms we have is actually a critical part of overall graph exploration and generating graph features. And so with that, again, we're going to, with that baseline, we're going to move into more the demonstration part of this workshop. Again, I know Alexander posted the link in the chat. Here it is again, GitHub/DanB Neo4j. There's one folder there for nodes 2022. All 3 notebooks are in there as well as the slides. And I encourage you to follow along either here on the live stream or with the notebook up as well. So before we jump into that, we'll talk a little bit about the scenario. I mentioned the Titanic data set before, and I'm a big fan of Kaggle. So I wanted to go out and get a different data set, not something that's really inherently graphy. And so I decided to use the Spaceship Titanic data set on Kaggle. This is a new expanded version of the existing Titanic data set. The one they have is about the Titanic that sunk in the Atlantic Ocean about 100 years ago. And the goal was to predict which passengers survived and which ones unfortunately did not. With this updated version, the data set is about 10 times larger. There's more features. The data is a little messy, and there's just more to work with. It's actually a really fun data set. And the scenario is that this spaceship or Starship Titanic is traveling from one galaxy to another. And during that voyage, about half the passengers get transported into another galaxy. And as the investigators or data scientists, we have to analyze the passenger manifest and figure out who was transported and why, and build a model to try to predict which passengers would and wouldn't be transported. And as I just mentioned, part of the reason I picked this data set is on the surface, it's not inherently graphy. It's not an airports data set or a Twitter data set. And those are all great data sets. But often when we're working with customers, not only do they receive data that's in a tabular or a JSON format, we also have to work with them to help understand where are the graphs in this data? Where are the connections in this data just below the surface? And going through the work to prepare this session, that's a question I had to struggle with. And as we get into the graph data model, I went through many, many iterations of it before settling on the one we'll share today. And I thought that it kind of reflected what we do when we're working with our customers to figure out not only what's the data that they're working with, but then how does that translate into graph? And I thought that would be just a good, authentic representation of a lot of the work that we do. And so with that, let me just jump out of the presentation. And again, I'll move over to, here's the GitHub. And I'm actually going to share the notebooks directly from the GitHub. And Alexander, please let me know if there's trouble seeing the screen. I have it zoomed in pretty closely. But what we'll do is we'll go through the notebooks.
I think it looks good. But
okay, great, thanks.
Yeah.
As I mentioned before, I'm not going to be running the code live. I'll be doing some Cypher queries later on. But again, all of these notebooks have been fully executed. And since we have such a packed agenda, I didn't want to be sitting here waiting for the code to run or debugging any errors. And again, follow along with the notebook, but really think about the high level concepts and how how they could fit into your workflow with the data that you're working with, the business problems that you're working with. But I hope these can be a resource going forward, and maybe after the fact, dig into the code as well. I'm going to cover them at a high level, not going to go line by line through the code, but that's something I definitely encourage. And if there's any follow-up questions, we'll try to get to them here, but if not, feel free to reach out in the Discord or elsewhere after the session. And so we'll start with this. Again, this is a tabular EDA notebook. So you'll see a lot of techniques and approaches that are similar to what you might have learned as you were learning data science or data analysis. So we'll skip through. We have some libraries, some pretty standard libraries. There's a lot of custom functions here that they're all documented at the top of the code. So I'm going to skip through those as well. But feel free to leverage them if you think it might be something that applies. Just having those functions, it reduces the chances of errors. It follows the don't repeat yourself principle. So we'll start with just loading in the data. And I mentioned this a little bit earlier. One of the most important things you do early on. So when we're taking a look at data from an exploratory perspective, we want to start with the data as a whole and then narrow down on individual elements of the data. I mentioned that I started my career as a forensic accountant and an intelligence analyst. And as an analyst, we're taught to use structured analysis. And by structured analysis, start with a problem as a whole, break it into individual parts, analyze each part sufficiently and thoroughly, and then bring the whole back together to for your analytic question or your total analysis. That's a similar approach here. We'll look at the data as a whole, and then we'll start focusing and focusing and focusing until we get down to each individual feature, and then bring it all back together for our total data understanding. And so the first piece of that is understanding what are the features in our data. This is a Kaggle data set. So we are fortunate to have a nice data dictionary. But as many people know, getting a good data dictionary or well-documented data in industry or in government or any of the other sectors can be difficult. It's not a technical task that you have to go through, but it is critically important to understand the features in the data as well as the contents of each feature. And I know I mentioned it before, but I really can't push that point enough. You have to understand the data that you're working with. And so from there, we'll just use, we have a pandas data frame. So there's a lot of methods we can use, just getting a summary of our data frame. And also one other point, the data has already been split by Kaggle into a training and test set. I know from working with the data that the ideas that we see in the training data set are mirrored in the test set. So for just to streamline the presentation, we're going to be focusing on the training data here. I'm just intentionally ignoring the test data set, but know that the insights that we see definitely carry over from the training to the test. And so here we'll get a summary of the data frame, and you can see by the non-null count, we already know we have some missing data. We have strings, we have numerics, we have some Boolean values, and even here, we can see just a summary of the data from a passenger ID all the way over to the Boolean of whether or not the passenger was transported to another dimension. We have some numeric values here. So generally what we would expect from a tabular data set. And so the first thing we're going to do is take a look at some statistics, some high-level statistics about our data. And we can do this with both the numeric and the categorical data. And so if we take a look at the categories, we can see passenger ID. This will be really important going forward. We need some sort of a unique identifier. And as we're looking at these, these are the categorical features. We know that when we're creating a graph data model, our nodes are typically nouns. And so, if these are the nouns in our data, we want to think about which of these features might translate to being nodes in our data set, which of these might translate to being properties on those nodes, and which might translate to being the relationships among the nodes. We want to have this in mind as we're going through the EDA. We know that there's a really good likelihood that we're going to convert this data into the graph format. And so as we're exploring the data and understanding the data, what is going to become a node? What's going to become a property? What's going to become a relationship? And we'll hit on that as we're going through the workflow. But at a high level, we have passenger ID, a natural unique property, a unique identifier. We have the home planet. This is where did the passenger originate from, kind of like a port of embarkation from the original Kaggle data. We have three of these home planets, so not a high cardinality feature. And the most common is Earth, followed by, I think there'll be two others. We have cryosleep. Was the passenger put into cryosleep during the voyage? It's an object here, but this is really actually a Boolean value, and it's a true-false. It looks like with about half, maybe more than half of the passengers not in cryosleep. We have passenger cabins. It looks like there's, it's not a totally unique value, which would make sense. A lot of passengers travel in groups of 2 or more. We also have the destination. Where's the passenger traveling to? Just like the home planet, we have 3 of these. And this TRAPPIST-1E is the most common. We have VIP status. Was the passenger a VIP on the ship? Another Boolean, true, false, and it looks like most passengers were not VIPs. And finally, the passenger name. And we can see here that we have, looks like we have some duplicates. We have some missing values and some duplicates again in the data. That could be a data quality issue. Well, when we get to passenger name, we need to see, do we need to make some changes because passenger names were accidentally duplicated? And we'll do the same thing with the numeric features, get a high-level statistical view of the data that we're working with. Before we had nouns, maybe some adjectives. Here, similar, we have the age, how old the passenger was, pretty straightforward. And then we have these 5 spending categories. These are 5 locations on the ship where passengers can spend money. And looking at the statistics here, it looks like roughly half the passengers really didn't spend much money. But those who did, we can see with the maximum value, really big spending, almost $30,000, $20,000 to $30,000 for the top end. And with the average being, below 500, we can see this data is heavily skewed. And not only that, we have the age variable that's on one scale, the spending on another scale. So depending on what type of modeling we want to do, we might have to do some scaling or standardizing of our numeric features. Just some high-level things, nothing we need to do right now, but something to keep in mind as we're going through the rest of the data. The next thing we want to look, again, we're looking at the data as a whole. Are there values missing? Now, this is a toy data set from a Kaggle competition, and it's unlikely that in the real world you're going to have a data set with 2% of values missing from all of the features. But that's what we have here, and so we know that we're going to have to do some imputation or throw out some data, or else it might cause errors with any machine learning models we run. One of the libraries I like to use is Missingo, and this will actually create a visualization of the missing data. And that's really useful to understand the nature of how data is missing. You can see here that the dark areas are where we have data, the white lines are where data is missing. And you can run this sorting on different values just to see if there's any correlations among the missing data. And what we can see here is that the data is really not correlated. So we don't have, if you're missing X, you're also missing Y, nothing like that. So we'll say the data is missing at random. and we don't really need to do anything special when we do when we impute values into the data. The same library also lets you plot a heat map, which will give you a little bit more of a precise analysis of whether or not there's correlations among the missing data. And we can see here that there's no correlations. If there were, we would see some numeric counts. We also want to see, are we missing duplicate records? Or do we have duplicate records? We don't, so nothing we need to worry about there. So we started really broad. Now we're going to start focusing on the features. First, we'll analyze the categorical features, and then we'll move on to the numeric features. And again, we're going through this in detail because EDA on the data in the current form will help us create an effective graph data model, and then inform any steps we need to take to prepare the data for moving into Neo4j. So that's, we're going to go through this workflow, reviewing what general EDA is, but with an eye and with kind of a twist towards how is this going to translate into graph. And so we'll start with our target value. We know that we're trying to predict whether or not a passenger was transported into another galaxy. So we have labeled data, the label is transported, true or false. And we know from the data dictionary that about half the passengers were transported. When we plot it out here, we can see it's almost 50-50. Looks like there's a few more than not, but effectively 50-50. And there's not really much we need to do because we don't have missing data here. But as we move into graph, we'll probably want to have this as, it could potentially be a node, but more likely it'll be a property on, we'll almost certainly have a node for passengers because all of this is passenger data. And transported, we can make a node. It'll probably be a property on the passenger node. Now, something we will want to consider as we're analyzing the data is how does transported interact with the other features? When I'm looking at another feature, how does that reflect passengers who were or were not transported? And we have some functions and some code to do that along the way. The next one is the passenger ID. This is our unique identifier. We have a good data dictionary, so we know that these passenger IDs are actually concatenations. We have a passenger group, which is the first 4 digits, and then the passenger number, which comes after the underscore. And so this is each value is unique. There's no missing data. And so we'll almost certainly use this as a unique identifier when we move into graph format. But what we can also do is some feature engineering. And as we go through the different features, where we need to do imputation or feature engineering to streamline the workflow, I'm going to do it at the point. A lot of people will do EDA, then imputation, then feature engineering. There's no right or wrong way to do it, but I'm going to do everything together with each feature as we go through the workflow. So what we can actually do with this is first we can create a passenger group feature, and this is actually going to get a little bit into the network or the relationships among the data. Each passenger is part of a group. And so that right there is an inherent relationship in the data. You have passenger to group. And we have some code here that it'll split it out and create passenger groups. And we see we have about 6,200 unique groups. What that tells us off the bat is a lot of passengers are traveling alone, but we have about 2,000 groups with at least 2 or more passengers. We can also calculate a group size. We have the unique ID and the passenger group. We can iterate through the data and count how many passengers are in each group. And we'll do that. We have the code to do that here. And then just a little code that it's a little wrapper around Seaborn to create horizontal bar plots. And what we can see here is that, as we saw above, most passengers are traveling alone, but we have a lot of groups ranging from 2 all the way to 8. So it makes sense that we might want to connect passengers to group when we move into the graph database. The next feature we'll address is passenger name. We know we're missing about 2% of the values, and each name is a concatenation of both first name and last name. So what we'll do is we'll fill in no first name, no surname. It could be really any arbitrary value. But something to keep in mind is, when we fill in data here, and we move over to the graph, the values that we fill in could actually become supernodes or could somehow skew the data when we move it into graph. And this will be something we have to address later on, that if we're imputing 200 or 400 passengers with no first name, no surname, or if we're imputing cabins or other features in the data, those could become supernodes that would skew things later on. And that's something we'll keep in mind for down the road. So we'll impute these values, and then we'll also split them so we create a surname feature. A lot of these passengers are traveling in groups together, and so we could hypothesize that a lot of passengers might share a surname. And as we go through and analyze, we'll see that's actually the case. We have as many as 18 passengers sharing the same surname. Name is often or probably going to be a property on our passenger node. But we could see where we might want to analyze surnames and see if, for some reason, a lot of passengers with the same surname ended up being transported. We don't know that yet, but it could be something we analyze going forward. And we can run a few statistics on this and see that on average, somewhere between 3 and 4 passengers share the same surname. And as we saw above, as many as 18 passengers share a single surname. So these are interesting elements that could be something we explore more when we move into graph. Something we saw in the statistics above was that there's passengers with the same name. That could be coincidence. It could be an error or a mistake in the data. Here we're taking a look at 5 passengers, but with duplicate names. We can see right here they all have duplicate names. They're from the same home planet, which might lend it that they're duplicates. But at the same time, there's a lot of other different values, different destinations, different cabins, different spending patterns, even different transported status. And so right now, it could be something that we need to look in. Maybe we go back to the business owner or whoever is responsible for collecting the data and validate that these names are actually just duplicates by chance. But for right now, for our purposes, we'll probably just leave it as is, because there's enough other differentiation that it's not clear cut that these are mistakes in the data. The next feature we're going to take a look at is the cabin. Each passenger is assigned to a cabin, at least, and the cabin has at least one, if not as many as 8 different passengers traveling in the same cabin. And we have the nice data dictionary, so we can see that just like the ID, the cabin is a concatenation of the spaceship deck, the cabin number, and the cabin side. And so, we can think about, we'll want to split that up potentially and analyze each piece of individually. Now, to fill missing values, this is interesting because passengers are assigned to cabins. If we impute a dummy value or an arbitrary value into the data, that could also become a supernode. And we know that passengers are traveling groups and they're from the same planet, they have the same last name. And so it lends itself to think that passengers might be in the same cabin together. And so what I have, and the code is at the top of the notebook, we actually have a function to fill in or to forward fill or backfill the cabin based upon other members of the group. And so what the code does behind the scenes is it takes all the passengers in a group, and anyone who's missing a cabin, it imputes a value from another passenger who's nearby in the group. It either fills forwards or fills backwards. And if all the passengers in a group are missing the cabin value, then it will impute the arbitrary F999P. And we picked that because F is the most common deck, 999 is a totally arbitrary number, and port was also the most common side. So that's kind of explaining how the imputation is going. It's not as fancy as like KNN imputation or using mice or something like that, but it's pretty straightforward and does the trick for this data. So we'll fill that in, and we're doing that now because if we want to go through and split the values and create a cabin deck, a cabin number, and a cabin side feature, we need to have the data imputed so we can do that split. And we'll do that. That's what we'll do here. We'll split those out. And then we'll also remove the slashes because we don't really need them. And sometimes they can cause issues down the road. We know that having special characters, whether it's here, some of the destination planets have spaces and special characters. It's just as easy. We want to remove those if we don't absolutely need them because they can cause problems. And just like before, we want to see, okay, where are passengers on the deck? We have these 8 or 9 different decks, and we want to count the number of passengers, and we can see some interesting patterns, but also patterns that we would expect. It looks like we have some of the higher decks might be analogous to business class or first class on an airline. Fewer passengers, maybe a little bit more expensive. But then we also have these other classes where we have a lot of the passengers. Almost half the passengers are on decks F and G. And then we have this T deck that with very, very few passengers. It could be a VIP deck. It could be something with the crew. It could be something different. So, but then if we also take a look at passengers who are transported based on the deck, remember we transported is our target variable, and we want to know, okay, how do these different features correlate or associate with whether or not a passenger was transported? And this is just another function that's at the top of the notebook. It plots how many passengers were transported from a specific categorical variable. And we can see that decks C and B have by far the largest percentage of passengers transported, whereas D and E seem to have much lower percentages. And again, this is important. Cabin, it could be a property on a passenger node. It might be its own node in the data set. And we want to know, same with cabin deck and cabin side. And something like what percentage of passengers were transported could be an interesting property that we include when we generate the graph data model. We'll do the same thing with the cabin side. As would be expected, it's split 50-50 as far as the count of passengers. And when we look at passengers who are transported, it's still it's pretty close to 50-50. It looks like starboard has a little bit above 50 and port a little bit below 50%. So we'll jump to the home planet. Each passenger originates from one of 3 different home planets. And just like the other features, we can think, okay, home planet's a noun. We have 3, it's not a high cardinality variable. We could have this as a property on a passenger node, or we could even have home planet as its own node in the data set and show passenger originates from or departs from a specific home planet. Ideas that we want to keep in mind and make some notes and whiteboard as we're building our graph data model. If we plot the count of passengers by home planet, we can see Earth is by far the most frequent. Europa and then Mars are second and third. But if we flip it and take a look at the passengers who are transported, we can see that Europa has by far the most passengers who are transported to another planet. Why? We don't really know right now, but we know that this definitely correlates. Mars is just over 50%, and then Earth, even though it has by far the most passengers, they're almost 10% less likely to be transported when taken in aggregate. And part of our additional analysis will be, okay, why? What's the correlation between home planet and transported, and are there underlying factors that lead to this? Same with the destination. Like I mentioned before, we're going to strip out the non-alphanumeric characters. We don't really need them, and it just makes it easier to work with the string data. We're going to impute values based upon using the same tools as above. Organize passengers by group, impute the value from the group, and then take a look at the analysis. We can see that this TRAPPIST-1E is by far the most popular destination, with far, far fewer passengers going to 55 Cancerie and this PSOJ location as well. Taking a look at the percentage of passengers who are transported, on the flip side, the 55 Cancerie has over 60% of passengers transported, with, again, TRAPPIST, the most common destination, also having the least likely or the lowest percentage of passengers being transported, though it's still pretty close to 50. This doesn't seem to be as impactful as a variable as some of the others might be. And just like with home planet, destination could be a property on a passenger node. It could also potentially be its own node in the data. We'll have to decide when we're building our graph data model. Cryosleep. This is a kind of a descriptor, whether or not a passenger was put into cryosleep during the voyage. Now, an interesting point that they make is that passengers who in cryosleep are confined to their cabins. When we start looking at some of the other features, this will be an important variable or an important descriptor that will affect values in the rest of the data. If we take a look, it seems that about 1/3 of passengers were put into cryosleep. But when we look at the transported amounts, those who were put into cryosleep, almost 80% of them were transported into another dimension. So this is clearly a very important variable and something we'll want to keep in mind. It's a Boolean, and we often don't use Booleans as nodes in the data, but it could certainly become a property on the passenger node. Finally, VIP status. We'll fill the data just like we were looking at the others. And we can see that very few passengers have VIP status on the ship. Maybe 200, if even that. But when we look at how they're transported, it looks like passengers who are VIPs have about a 12 to 14% lower likelihood of being transported compared to the rest of the population. Now, is that because of the deck that they're on or some other behaviors? We're not sure. So this feature, we don't have to bring all of the data into the graph data model. And this one, it looks like it's an extremely imbalanced feature, and the amount of information it's containing doesn't seem to be overwhelming. So if we include it, it'll probably be a property on the passenger node. But if we don't want to overload the passenger node with properties, this might be one that we just leave in the tabular form and don't bring into the graph data model. We'll have to decide that when we get to that point. And so that's all the categorical variables. And as we were going through, we have a pretty good understanding of the data now. And we also have a few ideas as far as what features are going to become nodes, what features are going to be properties, and how we might start building out relationships. And that's, again, why we're spending so much time on this notebook is EDA on the data as is informs our graph data model. And when we're working with customers, if we see that there's some challenges with their analysis or their modeling when the data is in graph format, many times it goes back to there's an issue with the graph data model and maybe something they didn't understand, or the graph model wasn't optimized for the data. And so doing the work up front, as one of my coworkers says, he said, you can do the EDA right now, by choice, or you can come back to it in tiers when everything you were working at didn't work out. And so it's better to just put the effort in up front, have a well-informed graph data model, and then be able to move forward with your analysis. So we're spending a lot of time right now to do everything possible to avoid issues down the road where we have to go back and refactor the data or make a lot of changes and then lose time on our project. And so that wraps up the categorical features. Next, we're going to move on to the numeric features, and we're getting towards the end of this notebook. We have 6 different numeric features. We have age, and then we have the 5 locations on the ship where passengers can spend. Now, we know that there's 2% of the data for each of these features is missing. And rather than do some, KNN or something else, we're just going to impute the median for all of these values. And so for age, we know that the mean is 29, the median is 27. So we'll just impute 27 and keep it pretty simple. For rooms, for the spending categories, the median is actually 0. And so we know because these features are correlated with some of the others, it's unlikely that we're going to impute something that would throw off like a logical element of the data. We'll just be imputing 0, and we'll just keep it really straightforward there. Also, as we saw before, the data is heavily skewed, and so that's why we're not imputing the mean, and we didn't want to have a passenger who didn't spend at all actually now have spending, show spending on the ship when they didn't in the first place. So the median keeps it really simple. We'll start with the age feature. This is the age of the passenger. We can see that it ranges from 0 to 79. And this function here, this is just a little function that creates a data frame where it shows all of the data, and then it splits it out between transported and non-transported. And I wrote it just to make it easier to analyze numeric features in this data or any other. And so we can see, we have the plots below, but we can see that passengers who were transported seem to be a little bit younger than passengers who weren't transported. And that also is here in, we have this is just another little seaborne wrapper where we're plotting a histogram showing the passenger age and overlaying transported and non-transported. And we can see that transported tends to land a little bit younger, and then around middle, from the 20s to the 40s. Not transported is a little bit more common, and then they're roughly even through the rest of the data. The next thing we'll do is approach the onboard spend categories. And in the data as is, we have each of these 5 categories on their own. And so a natural approach, one of the first things we can do is just add them up and create a total spend feature for each passenger. And since this is passenger data, both age that we just looked at and then total spend right now, these will probably be properties on the passenger node. Both age may or may not be important. We're not sure yet. But total spend, because there's 5 other features, we can aggregate those and just have one value potentially on the passenger node, summarizing a lot of information in the data. So we'll add it all up and then take a look at some of the high level, all the passengers, those who were transported, and then those who were not. And we can see that we have a big range in the data that we were seeing before. And once we aggregate the data, it's interesting that now the median is about $716, whereas before, when looking at each of the features individually, the medians were all 0. And so we can see that roughly half the passengers spent at least a little bit of money on the ship. And that makes sense if you kind of think of this as analogous to a cruise ship. You pay to get on the ship, and then you spend a lot of money when you're on it. But otherwise, we can see that passengers who are transported appear to have spent a little bit less overall. And that actually makes sense if we think back to passengers in cryo sleep. Most of them, nearly all of them, were transported, but they were confined to their cabins. And so, naturally, they couldn't spend money. And if we plot it out, again, we can see we have transported spent a little bit less than those who were not, all across the data. And so real quickly, we'll move through these 5 spend categories. We can see here, there's some really big swings. Room service, passengers who are transported, even the maximum values are far less than those who are not. And this might be a trend in our data that we want to consider going forward. Same with the food court. It looks like we actually did have at least one big spender, though very few passengers spent overall. There's a lot of zeros going through the quartiles. We have the shopping mall. It actually looks like some passengers who were transported spent heavily there. The spa is another one with a big difference. The max spending was in the not transported category. We have almost nothing until we have at least one passenger spent $4,000 and was also transported. And finally, the VR deck, again, a similar major difference in the data between those who were transported and those who were not. Now, these are, these features, this will be interesting. We need to figure out how we want to incorporate this into our graph data model. It looks like there's a lot of information based on passenger spend, but we don't want to overload the passenger node with just all these different numeric values. We may want to do some feature engineering or figure something out. And that's, as we get to our data model shortly, we need to figure out how do we incorporate this data into the graph itself. Last thing we want to do is make sure we don't have any logical inconsistencies. We know if a passenger was in cryosleep, they're confined to their cabin and they shouldn't be spending on the ship. So what we'll do is we'll check, are there any passengers in cryosleep who also spent money? If that's the case, we know that we didn't impute any values other than 0. So it might be a mistake in the data, and we'll just set their cryosleep status to false. If this weren't a competition, this would be something where we go back to the business owner and then see if there might have been an error or a mistake in the data. But given the context we're working with here, we'll just go ahead and flip their label from true to false when it comes to cryosleep. We also know that passengers share home planets. They're traveling in groups on cabin decks. And we know that we imputed some values which might throw off other logical or existing patterns in the data. And one of those is passengers from the same home planet travel together on the same cabin deck. That's something I know from working with this data. I'm cheating a little bit here, but we know that imputing the home planet of Earth, which was the most common, will actually create some logical inconsistencies. And so what we're actually going to do is passengers on a couple of decks where we have Earth, we're actually going to switch their home planet to Europa because that's where all the other passengers on those decks are from. Imputation is not perfect. More often than not, it adds more benefits than not, but where we can see there's mistakes, we may as well just go ahead and fix those. Same with passenger groups and cabin side. We know that passengers in the same group also travel on the same side of the ship. We want to make sure that there's no errors there, and there's not. We're almost done with this notebook. The last thing we're going to do real quick is something I alluded to early on, is we're going to train a model as part of our EDA. In this case, we're just going to train a quick random forest, and we're going to use it for the model to tell us what are the most important features in the data. We have an intuition from our analysis here, but it doesn't hurt to let the model tell us what it thinks as well. And so we're going to go through, I'm going to go really quickly through this part. This is a standard machine learning pipeline. One hot encoding for our categorical features. We're going to use home planet, cryosleep, destination, VIP, cabin deck, and cabin side as the categoricals. We'll use pandas get dummies to one hot encode them. And then we'll also include all of our numeric or quantitative features, split them into training and labels, and then we'll train a random forest model. These are some hyperparameters that I know get us a model right around 80% accuracy. And we don't really care about the accuracy at this point as long as it's not way off. What's most important is this chart right here, the feature importances. And this is just, again, a great process to use with almost any analysis project, is throw it into a random forest or something similar and see what does the model say the feature importance is. And we can see that the total spend feature that we created is actually by far the most important variable. So we definitely want to incorporate this into our graph data model. The second most important feature, interestingly, is spending on the spa. And that's one where we saw there was a huge difference between passengers who were and were not transported. The third most important feature, which is very surprising to me, is actually cryosleep. And that's because we saw before that more than 80% of the passengers in cryosleep were actually transported. It's basically a label where you transported. And then all of the other features show declining importance. We have the cabin deck. Cabin deck is important, but not overly so. All of the spending features are very important. And this is really useful because if we were thinking we might or might not include a certain feature in the graph data, this might help make the decision if we were kind of on the fence about something. And with that, that's the rest of this notebook. Again, this is published. I'm looking at it right from GitHub. I would encourage you to revisit it if you're so inclined after this workshop. And if there's anything that you find useful, by all means, use it, improve it. If you see any mistakes, please let me know. But this is just a good high-level EDA notebook. And from there, the next step, as we were talking about before, is going to be, let me go through the slides, building our graph data model. I don't really have slides. I can actually go straight to arrows. So we have a deep understanding, we have a really good understanding of our data in its current form. Now we need to figure out, okay, how do we translate it into graph? And I can tell you, having done this, preparing the workshop, I went through a lot of iterations of this. And I had graph data models that were twice as big, that were smaller, before landing on this. And this is the graph data model you create is going to be unique to your data and your use case, and so this is in no way prescriptive of what a data model should be, but it's a good starting point for this data set and our business question, which is what passengers were transported and why? How do we predict which passengers were transported? And as we talked about before, this is passenger data. So we wanted to start with the passenger node. And we decided to include a couple of properties. We have the age, we have the total spend, which was far and away the most important feature. We have a unique ID, which is the passenger ID. And we have transported, which was our target variable. And then whether or not the passenger was in cryosleep. 5 properties on a node is, circumstances aside, probably the upper end of how many you want. It's not really a hard and fast rule, but this is probably as many as we would want to include. We are fortunate this is a small data set, and so we won't be taxing the database too much. From there, we take a look at the planets, and we have 6 unique planets in our data. 3 of them are home planets, 3 are destinations. And we know that there's some variation, but there's definitely ones that have far more passengers than others. Rather than add that as a property to the passenger node, instead we can have just a planet node with 2 types of relationships. And it's a little tricky to see right here. Let me see if I can, if you need me to zoom in, I can a little bit. We have traveling and originated. And it's a little tough to see there, but in some of the models, I actually split it out. I had a home planet and a destination planet. But to keep it simple, we actually have just one type of planet node with 2 types of relationships going to it. From there, we created the surname feature in our data, but we didn't use it in our model. And this is because it's a more of a high cardinality value. We have several thousand unique surnames in the data. And this also applies to group, which we have, I think, over 6,000, and cabin, which I believe is also almost 6,000 different cabins. We weren't able to use some of these high cardinality features, but we wanted to include them because they're a little bit more easier to work with in the graph. And so we connected the passenger. Each passenger has a surname, and that's the type of relationship we'll create. We also have each passenger is the member of a group. Now, a caveat to that here is we're only including groups that have 2 or more passengers. By definition, every passenger is a group of at least 1. But a passenger just traveling in a group by themselves doesn't really tell us anything we don't know. So we're going to have groups, and we're going to give it a property of how many members are in that group, and it's going to be 2 or more. Each passenger is also assigned to a cabin. And again, we'll have that as a feature. Oh, before I forget, we also because we want to see some of the relationships in the data, we're going to take a look at what surnames are in different groups, because we have at most, I believe, 4 passengers share the same surname. I'm sorry, no, 18 passengers share the same surname. But if they're spread out across different groups, is there any connection or relationship between passengers, surnames, and groups? That can be a little tricky to analyze in a tabular format, but as we'll see, kind of tipping my hand a little bit, it's more straightforward and kind of easy to analyze when we're using the graph data. So we have each passenger assigned to a cabin, and then rather than have properties, we created a cabin deck node and a cabin side node. I know I mentioned before, we typically don't create nodes where it's just 2 values. It's like a Boolean or port starboard. In this case, we're not traversing. It's a small data set, and we're not traversing through cabin side. It's kind of an end node in our data, so we're okay with it there. And then cabin deck, there's 8 different values. Finally, we have the amenities. We know there's 5 different onboard amenities that each passenger can spend on. And so each amenity is going to be its own node. It's going to be an amenity node with a label, VR deck, room service, shopping mall, etc. And the relationship is going to be the amount the passenger spend. So we're going to have if the passenger spent any money at the amenity, we'll create a relationship, and then we'll have a property on that relationship with the amount they spent. So it's almost a weighted relationship. And so this is our graph data model. And it's interesting to see that originally the graph was not really the data was not really graphy, but now we've actually created a model with 8 types of nodes, 9 different relationships, and there's far more we could do, but this is a good starting point. We don't have to have everything in the graph, and this will hopefully give us some insights to figuring out why certain passengers were transported and others won't. And so with that, we're actually going to jump to the next notebook. There we go. Okay, all right, we're zoomed in, and this is the second notebook. This is the loading the graph data. We're not going to spend a ton of time on this notebook, but I did want to go through the exercise of converting the data from tabular format into the graph, because there are still more elements that tie into our exploratory data analysis, and this is a point where we actually start some of our graph EDA as well once we load the data. So we'll jump in. I'm going to skip through the standard Python libraries. We have some custom functions here. This one is a nice one where it will read if you're using Aura like I am for this exercise, it'll read your connection and property or password and username from a file, so you don't have to save it in a notebook. Never a good practice. And then there's a lot of functions here where it just speeds up and makes it easier and more consistent to convert, to create node lists and edge lists. And I'm speaking from experience where when I was doing it manually and I didn't have the functions written, I was making a lot of mistakes, and I kept having to go back and delete the database, reload the database. Having these types of functions, in addition to don't repeat yourself, it also just reduces the chance for user error, which on my part there's plenty of user error. So we'll load in our data set. This is the data that we outputted from the last notebook. It doesn't have all the machine learning one-hot encoded variables. It's the data up until that point. So you can see, we have surname, cabin deck, total spend. All of these features we spent time creating before. And even if you go back to the graph data model, some of our nodes and properties like surname and total spend and cabin side, cabin deck, we created these properties. We created these features in the data. So if we were just using the data as is and we hadn't gotten that understanding, we wouldn't be creating these nodes in our database. Again, tying back to the iterative nature of these steps and the importance of understanding your data. Using Aura right here, absolutely love it. It's just ready to go. You don't have to do any configuration. Absolutely love it. If necessary, clear out any data that's in there. And then we're working with a really small data set here. So it loads pretty quickly, but with larger data sets, you want to make sure you understand what elements of your data are going to be unique, or what's the unique key. And having that understanding of the data will help you create constraints which can prevent accidentally uploading duplicate data and speed up the overall data ingestion. So definitely worthwhile to include these. Can quickly show constraints. And then we'll start loading our data. So we're going to do all of this from the notebook. You can certainly use the data loader. You can use pure Cipher in the browser. For this case, I'm trying to do everything through the notebook. It's where I like to work as a data scientist, and I know a lot of people share that idea. So we'll create we'll get the passenger features that we want. We have the ID, age, cryosleep, total spend, and whether or not they were transported. And the way we're going to do this is we're going to pass lists of dictionaries or lists of hash maps to the cipher code. And so I'm just giving just a little example of what the data is going to look like as it's being read into the database, just to so you have an idea. And we'll do that here. We're using the GDS Python library, and we're running cipher code right from the notebook. We're going to pass in a passenger list. We're calling it passenger list, and we're defining it as our data frame, selecting just those features that we want. And then we're using the pandas to dict, which will convert it to a dictionary. And there's multiple types of dictionaries. We're going to use records. And so if you look at Neo4j code or code that's on GitHub, you'll see a lot of people use this. We pass it in with the $sign. So we're unwinding the passenger list. It's a list of dictionaries. We're going to merge on the ID. This is our unique ID. And then as the node is created, we're going to set the 4 additional properties: age, cryo, total spend, and transported. And you also want to make sure you have the right type of data. Cryo, sleep, and transported, those are Booleans. And then if we want to work with some of the algorithms later on, we want to have the numeric values as floats. They're either going to be integers or floats in our data, but we want to make sure that we have the proper data types when we're ingesting the data as well. And we're just going to go through all of this. I'm not going to spend too much time. We have a list of the planets. We're going to unwind that list and create the planets. We're going to create the surnames. We'll do the same with groups, but again, we're creating a feature here. We're going to create a variable here because we only want groups with 2 or more members. And with that, we're going to include the passenger group ID, or the group number, and then the group size. And just like the other features, we'll unwind it and upload it into the database. We'll get a unique list of cabin nodes, upload those. We have the cabin deck, we have the cabin side, and then the amenities, we'll just hard code the 5 different amenities here. And then we move on to the relationships. And here, going back to our data model, we want to make sure we replicate each of the both the directionality and the source and target of each of the relationship. And so I included a little bit of cipher code with each one, just to remind ourselves what relationships we're creating. And we'll be creating edge lists here, where here's an example. We have the source and the target, and we'll go ahead and unwind these relationships, match on source, match on target, and then merge and create the relationship. And we'll go through with the traveling. We have passengers traveling from and to. Passengers have surnames. They're members of groups. Again, remembering that we're only pulling in groups with 2 or more members. Each passenger is assigned to a cabin, and then each passenger is spending on an amenity. And this is a situation where I was running into a bunch of errors. So I just wrote custom code. It's a function that's at the top of the notebook where you pass in the data frame and then the specific column, and it creates an edge list where the amount is going to be the property. And this is the only edge we have that has a property. So we go ahead, we create those edge lists, we combine them, and then just in one cipher statement, we can upload all of the relationships. And then finally, we have the cabin on the deck and the cabin on a specific side of the ship. Oh, and then finally, surname into group. Now, one thing I want to do here, and this is where we're going to start moving from EDA and data formatting and loading into our graph EDA. Having gone through it myself and worked with a lot of, we work with a lot of customers who sometimes have these challenges. You want to make sure that the data in the graph database matches what you expect it to be, that there's no hiccups along the way. Just whether it's code or something else, sometimes there's just little mistakes. And I've heard this called kind of defensive coding, where we're going to have a bunch of assert statements to make sure that the values in the database match what we expected from the source data. Just checks in a database, kind of standard process if you're managing any sort of a database. And so what we're going to do, or what I do here, is call apoc.meta.stats. This is a function from the apoc library, and it returns a table which we save as a data frame. And we go through, and that table coming from Neo will tell us, okay, this is the data, these are the nodes and the relationships that Neo4j sees in the database. And we want to run some assert statements just to make sure that the node counts match up, the relationship counts match up. And if you run through this, all of this will tell us that we are good to go. But having that, that summary data frame from apoc.meta.stats is really useful. And we'll spend a little bit more time with it in the next notebook. But so that wraps up the data loading notebook. Didn't want to spend too much time on it, but it's a very important part of the process, and also just a very iterative part of the process where, something about, you build a data model, you load the data, it might not be what you thought it, so you go back, refactor the data model, maybe even go back to the source data. A very fluid, iterative process, to say the least. And with that, we're going to jump to the third notebook, the actual getting to the graph EDA portion of the presentation. Though I will say, just running those basic checks is almost, it's a starting point for our exploratory data analysis. And with this notebook, let me see, I don't think I have any slides. Yeah, no additional slides to cover here. We'll just jump right into the notebook. With this part of the process, it's not going to be just notebook based, because there are, I love Jupyter notebooks. There's a ton of great things you can do, but especially when you're visualizing graph data, it can be tricky. And that's where the Neo4j platform has outstanding features. The Neo4j browser and Bloom, both of which, especially Bloom, is great for exploring our graph in a visual way. And really in a GUI interface, you don't have to use any code. So we'll get to those as well as part of this process. So with that, we'll jump into the notebook, some standard libraries as before, some standard custom functions. I'll mention these when we get to them. A lot of them make it a lot easier to work with that apoc.meta.stats data frame. Some of them are also just one-liners that are wrappers for Cypher code. It just helps make the notebook a little bit more streamlined and easier to work with. I built all this on Collab. We don't have to worry about that right here. Similar, connecting to Aura. So as a data scientist, I love that because there's not a lot of configuration. And so with that, we're going to, one of the first things that you should always do is visualize the schema of your data. And let me jump into the browser. Oh, looks like I'm still logged in. That's good. The first thing really that we always recommend is a call db.schema.visualization. And that is basically asking Neo4j, show me what the data looks like to you. Show me what the schema of the data looks like. And I'll zoom in here in 1 second. We want to make sure that this is similar to what we had in our data model. And thankfully, our data model is pretty small. But if we zoom in, we can see it's almost identical to what we had in arrows. If I'll jump back to arrows real quick, we can see we have passengers, planets, amenities, cabin. And if we move over to what the database is telling us how it sees the data now that we've loaded it, it's identical. And that's really good to know. We know that the relationships are in the right direction. So just like the assert statements we had before, we have the right node count, the right relationship counts. It also passes kind of the common sense test. It looks like what we expect it to look like. So no surprises there. The next thing we'll do is, again, from the notebook, though you could also, this is Cypher code, you could easily use it in the browser as well. We're going to call apoc.meta.stats again, and it returns just a a 1-row, 9-column data frame. And we display that here. Though you can see there's a lot of text, a lot going on. It's not the easiest to read through because there's a lot of relationship types and values. So rather than try to analyze this, there's some custom code in the notebook to just pull out and kind of summarize the information that we would want. And also going back to our original approach of going wide to narrow, we're going to start with a wide view of the database. We already know we have the right node counts, the right relationship counts. Now we want to dig a little bit deeper. So here we can see again, we have the nodes and relationship counts. These all add up. We'll focus on the nodes. How many of each different types of nodes do we have? And does it pass the checks we had before, as well as kind of the common sense test? 8693, we know this is the number of passengers in our training data. 6560, the count of cabins. Surnames were about, around 2200. Groups with 2 or more members was just under 1500. 8 decks, 6 planets, 5 amenities, 2 sides. Everything looks good. We have another function here that will pull in the properties. A lot of these, some of these nodes have a couple properties, others are just the ID. This function here is just a wrapper for the cipher code to pull that in. And we'll see amenity cabin. A lot of these only have an ID as the property, but we know group, we have group size, and then we know passenger. We have 5 different, whoops, I'm not sure what that was. We have 5 different properties as well as the planet. Now we know because we spent so much time on the EDA and we designed this data model, we know that we know what features or properties are in there. If for some reason you're working with a data set that you don't have a good understanding of, or you haven't been able to get a good explanation of the data or a data dictionary, a lot of these functions are really useful when you're kind of flying blind, which does happen. This is an ideal situation where we have a good, deep understanding of our data. That's not always the case, and I definitely want to acknowledge that. And actually, that was sort of the situation that led me to even create this workshop. Was I was working with a data set where I didn't have a data dictionary. I didn't have any background or explanation. And I had to figure out how to learn about the data in graph format on the fly. And that might be the situation where you're just dropped into a project or dropped into an engagement where you don't have a good understanding of the customer or the business unit's data. A lot of what we're working on here could translate to that situation where you don't have checksums, but you still need to understand what's the data you're working with as much as is possible. The next thing we're going to do, and this is something I alluded to before, is we're actually going to delete some supernodes. We imputed no surname for about 200 passengers where we didn't have their full name. That's going to create, we know that the maximum number in the data confirmed is 18 passengers sharing the same surname. So we don't want to have 200 or more sharing no surname. It's just going to throw off things. So we're going to go ahead and delete that node. And similarly, for the few hundred passengers who didn't have a cabin, or it's actually far fewer because we imputed based on groups, but there are still a lot of passengers with this F999P arbitrary cabin. Could throw off some of our analysis, so it's not essential and we can get away with it, so we're going to go ahead and delete that node as well. Then we'll move on to the relationships. Again, we already checked the numbers before, but we can see the distribution. Spending is the most common. We have 8,000 passengers spending on 5 different amenities or not spending. A lot of passengers assigned these different relationships. 8693, that's a number we know well. We have about just under 4,000 passengers who are members of these groups of 2 or more. And then we have 1,700, almost 1,800 relationships between surnames and groups. So if we go through the properties, we can see spending is the only one that actually has the only relationship with a property. Again, checks out with how we designed the data model. A lot of what was really messy in that summary data frame from apoc.meta.stats were these different relationship patterns. This is a function that just goes ahead and pulls them out and lists them with the relationship count. It's not the easiest to read through, but we can see the general patterns because they're broken up based on nodes and relationships. So it's really the same relationship here, but we can see passenger spending on amenity, the 15,083. So it just gives us some ideas about the patterns of relationships if we want to start exploring those, which is actually the next place we're going to go. And with that, we are going to jump over to Bloom. Oh, looks like I was locked out. Oops. Of course, this is happening live on the webinar, but that's okay. There we go. All right, and we're back in. So what we're going to do, so if you're not familiar with Bloom, Bloom is the built-in data visualization platform in Neo4j. And it's almost, I would argue it's almost custom made for exploratory graph analysis. You don't have to use any Cypher code or any other coding. It's point and click. And it really allows us to just see what's in our data and see what patterns we might want to explore further. There's a lot of additional features where you can filter relationships and even incorporating some of our graph algorithms and graph data science capabilities as the product evolves and more features are added to it. And so if you haven't worked with Bloom before, definitely recommend checking it out. If you're going to be working with data or visualizing data, it's also great for your counterparts who aren't as comfortable, say, with a notebook or Python or Cypher. They can still analyze graph data using this platform. It's these types of GUI interfaces are how I got started in data science before I could program a line of SQL or Python. So what we're actually going to do is explore just some of the relationships. We'll think about, we know that cabin was a high cardinality value. We know each passenger is assigned to a cabin. Each passenger has a surname. We have surnames in the groups. And so we can just string together a couple of these relationships and see how they play. Also, Bloom can even just suggest some relationship patterns, or you can type them in plain language. But I'm going to go through and just click through. We have, what am I looking for? I'm looking for cabin. And then we have passenger cabin. Each passenger is assigned to a cabin. Each passenger has a surname. And then many of the surnames are in a group, and we can string all this together and just see what it returns. Another benefit of Bloom, I love the Neo4j browser as well, but Bloom is designed to visualize the data, and so it can handle larger amounts of data. It helps avoid, it looks like we have a little bit of a hairball here. It helps avoid just so many nodes in the screen that you can't actually see anything meaningful. And so real quickly, I'm just going to zoom in, and we'll pull apart one of these little clusters. We see a lot of clusters, or you could call them communities or subgraphs. And we're looking at where are there a lot of relationships, or even just we hypothesize that this type of pattern where a passenger is connected to a cabin and a surname and a group. Do those relationships actually exist in the data in a way that would be meaningful to analyze further? So I'm going to jump up to this one's a little bit differentiated. We have a surname here, which is connected to a group, and we have a surname with a lot of passengers. Passengers are connected to the cabin. And so we're seeing that, a lot of these look similar, in that you have groups of, passengers and surnames and cabin. And so it's, it looks like we actually have one here where we have an interesting pattern. If we zoom in, we'll actually get some labels as well. We have this group. It looks like it's connecting two different surnames. So we have multiple surnames in the same group. And then with that, we have all these different passengers who are staying, and it looks like they're all traveling alone. So different surnames, so we're going to see different patterns in the data. And again, you could spend a lot of time here going through and analyzing what are the different patterns that, we could delete, we could filter. Actually, I'll do that real quick. I'm going to filter group. I'm going to go group size, and I only want to look at groups of 5 to 8. And we can do that dynamically and dismiss any group that has fewer than 5 members. And it looks like it thinned out our data just a little bit. I'm going to go look at this one. This looks like we have another pattern where we have this group is connecting 3 different surnames in the same group. Let me zoom in a little bit more. 1, 2, 3, all connected to the same group. And then a lot of passengers, looks like a lot of passengers are traveling in the same cabin with 3 different surnames. So that's telling us that we do have these inherent relationships in our data, a lot of intermingling in our data. So we can, this is an analytic path that we can dive forward with and do a little bit more analysis. And so that's just a really high level look at Bloom and how you can use it throughout especially the graph EDA process. It's a fantastic tool, and I highly, highly encourage you to think about if you aren't using Bloom already, how might you incorporate it into your workflow, where it makes sense and where you think it can add value. Definitely not something you want to sleep on. And so with that, we're going to actually move back to the browser. I absolutely love Bloom, but sometimes I use Bloom, sometimes I use browser, and just want to highlight different ways that you can perform some of this graph EDA. So what I'm going to do is actually mirror the pattern that we were just searching on and search for it in the browser, in Neo4j browser. So I have a little bit of Cypher code. I'm just going to copy over here. Here we have the pattern that we saw before, and I'm going to filter for groups of 5 where the group size is 5 or more and where the passengers were transported. Just adding that because if we go back to our analytic problem, we want to see, okay, why were passengers transported? And so we might want to focus on big patterns or big clusters or big communities of passengers who were transported to another dimension.
Can you zoom in a little bit into this window here?
No, thank you. Yeah, we'll do. Thank you. So this is the browser can be a little tricky to see here, but I'm going to zoom in on another cluster that we have, and you can see we have a couple of surnames here. Well, that was not intended. Let me log back in. And let me get that as well. Let me get the code as well. All right. All right, I'll zoom in here, and it might be a little difficult to see, and I do apologize for that. But we are seeing similar patterns in our data. And what I really just want to emphasize is that we're seeing these clusters of groups where, we have 5 or more passengers, we have the passengers were transported, and even though we're filtering on that, we're still seeing communities or clusters in the data. Here we have 2 different surnames, they're connected by a group, and we have a lot of passengers around it. And you might also see, there are some additional node properties that I created when I ran the notebook before. I'm not running the code live. There are some additional properties you might see, and we'll be explaining all of those as we go through the workflow. But again, the key point here is that we have, even when we're filtering for larger groups and only for passengers who are transported, we're still seeing clusters or communities. We want to just explore that now, and then we'll approach it more algorithmically or analytically as we go through our EDA process. And so going back to the notebook, when you're working with graphs, you need to think in graphs, and there's going to be different exploratory statistics that we want to analyze when we're working with graph data. And one of the first statistics is the node degree. Basically, how many connections does a specific node have? And we can approach this based on what we know the neighbors of the different nodes are because we designed the graph data model. For instance, if we take a look at the cabin, how many passengers are assigned to each cabin? And we did explore this a little bit in our traditional EDA, but we can also approach it here. And what I also want to show is that there's different ways to calculate this, and you might want to use one or the other based on the nature of your data. The first thing we can do is, again, we're just running a little bit of Cypher here, and we're using apoc.ag.statistics. Again, another function from the apoc library. And what it will do is it will return a very small data frame that has a dictionary nested in it. And so we just unpack that, and we can calculate really quickly in the database some statistics around passengers being assigned to cabins. Very straightforward. And then once we have it, there's not a lot of import and export from the data, so there's not a lot of cost there. And we get a lot of summary statistics showing a lot of what we knew before. We have at most 8 passengers in a cabin, a minimum of 1, at least, each cabin has at least 1 passenger in our data, with the average also being around 1 as well. What we can also do is, rather than using apoc.ag.statistics, we can calculate this data, get a list of the values, and then export the list of values back into the notebook. In this case, it's just a NumPy array with about 6,600 values. Nothing with a huge cost, though you might not want to do this if you're working on a graph database with 100 million or 500 million. The only reason we might do it is we have those values, and we can also do some plots. In this case, well, first here we have, we can generate some summary statistics using pandas, and then also generate some plots if we want to plot this data, and if the data set itself is not too big, we don't want to crash our Python server, or just have too much cost of importing huge amounts of data into and out of the database. How you handle it will definitely be based on your situation and the data set you're working with. We can also look at passengers with surnames. This is similar to what we had in our tabular data set. Going forward, because this is a small data set, I'm just going to return the values to Python, generate statistics in Python, and also generate some plots because we're able to do so. And it adds to the visual element of the database. How many passengers have different surnames. We can see the distribution aligns to what we thought about before. 3 to 4 is pretty common. 3 to 4 passengers have or share a surname, going all the way up to 18. Something that's unique to our graph data model now is how many passenger surnames are in each group. This isn't something that we had before. But with it could be almost 1 line of Cypher, I have it as 3. We can see how we have 1,400 surname or 1,400 records, and on average, we have about typically one surname per group. Again, this is skewed data because each group only has at least 2 or more members. And so what that tells us is there might be a lot of familial relationships in the groups, especially the smaller groups where everyone shares the same surname. Also would be expected on kind of something analogous to a cruise ship where groups of families are traveling together. Passengers being members of the groups. Again, these are only groups of 2 or more. We bring back the data as a NumPy array, and we can see the typical, the average is about 2 to 3, somewhere between 2 to 3 members for each group. And this also makes sense because we knew a lot of passengers were traveling solo, and then a lot of passengers were traveling in pairs. I would suspect this would mirror data that you might see on like a cruise ship from a cruise company. Again, we can see 2 to 3 is the most common, and then it dwindles all the way to 8 passengers in a group. So we were looking at some high-level statistics, high-level connectivity or connectivity statistics. Now we want to take a look at some of the different types of nodes. And in particular, we're going to take a look at the surname nodes, because this isn't something we did a lot of analysis before, but now that we have the nodes in our graph data set and the nodes are connected to passengers and groups, there could be some interesting information that's generated there. And we'll run a couple of Cypher queries here, and then we're going to move into projections and some of the algorithms as part of our EDA as well. So the first thing we want to know is how many distinct surnames are in groups. And we see about 1,200, just over 1,200 distinct surnames are also members of a group. So not all surnames, there's a fair number of passengers who aren't in groups, who have a surname that's therefore not in a group. Also, because of something we didn't analyze before, but again, we're going back to who was transported and who was not. And so we want to see how does surname associate with being transported? This is something we could have done in tabular format, but now that we have it in the graph data, it's pretty straightforward to calculate as well. And so what we have is some Cypher code that generates the surname, the count of passengers who have that surname, the count of passengers who are transported who have that surname, and the transported percentage. And as a result, we're going to do this for all of the surnames, about 2,200, and we're going to take a look at what are the top 5 surnames based on having people who have that surname being transported. And we can see there's a lot of these larger surname groups where all or nearly all the passengers were actually transported. Because we're digging into why are passengers transported, there might be something to having a specific surname we really don't understand. Now, correlation is not causation, but this could be an analytic avenue we want to explore as we dive further into the data. In addition to that, we can actually calculate how many surnames had all of their members transported. And we can see there are 444 surnames where everyone who has that surname in our data was transported to another dimension. We can also run some basic statistics. We brought this back as a pandas data frame. We could also pass it to apox.ag.statistics. And we can see that on average, again, each surname has about 3 or 4 members. The transported count is also, it's 2 to 3, so a little bit less. Not all people who have a surname are transported, so it makes sense. It's a little bit less than the total amount. And again, the average percentage is right around 50%, which is in line with the overall percentage in the data frame or in the database. We can see 50% is, for most surnames, roughly half the passengers were transported in line with the overall data. Something we can also do is now that we calculated the statistic, we can write it back to our database to use for further analysis, especially when we get into some of the algorithms. And so we'll do that here. We'll take the data frame, we use a similar coding pattern as before, and write these features back to the surname nodes. And we're going to do the same thing with group nodes. We're looking at we're looking at surnames and groups. And so we'll calculate some similar statistics for the groups. I'm not going to spend too much time on the code. It's very similar to what we use for the surnames. But what we're going to see is we have when we sort it by the count of passengers transported, we can see there's a lot of groups where 6 or 7 passengers total, and all of them or nearly all of them were also transported. Just under 400 groups had all their members transported. And we can see that we're looking at roughly 50%, 1 to 2 members transported, which would be in line because we have more groups that have 2 or 3 members than we do groups with 5, 6, 7, and 8. Similar 50% statistics, about half the passengers transported, 0, 50%, 1. This is in line with what we would expect because we have a lot of groups with 2, maybe 3 members. And just as before, we will write these properties back to the nodes so that we can use them for further analysis. And finally, we'll do the same with cabins. You can see that we're focusing on some of the high cardinality variables before that we couldn't use in our modeling, because if we used all the cabin numbers, all the surnames, all the passenger group numbers, we would have more features than we actually have data. And so we need to figure out, how can we analyze this data here, potentially compress it, retain the information, and take it back to our random forest or XGBoost or any other model that we're using. Similar statistics on the cabins. We have 7 passengers assigned, 7 passengers transported. A lot of cabins with high counts of passengers. We can actually see that in, when we calculate cabins where all occupants were transported, it's actually a really high number, but we have to remember we need to filter for cabins that have 2. If we filter for cabins with 2 or more passengers, the number drops down to closer to 400, which is similar to the surnames and the group count we saw before. So maybe there's some correlation between surnames, cabins, and passenger groups in having a lot of participants being transported. We'll run a few statistics, and again, we'll see what we see before: 0, 50%, and all. This data is a little bit skewed because we have single occupancy cabins. So if one person is transported, then by definition, everyone's transported. So it'll skew the data just a little bit. But again, as before, we'll just write these properties back to the nodes and continue moving forward. So what we can do again is start exploring the data. And I'm going to jump back to the browser and run a query where we're going to actually filter for surnames, groups, and passengers where we have a lot of members transported. And we're not going to dig too much into this, but you can see as I'll zoom in here, it might be a little tricky to see in the presentation, but if we zoom in, we can see where we have a surname, this Domington. It's connected to a bunch of different cabins and a lot of passengers. And going back to our code, this is high percent, larger groups where nearly either all the cabin occupants or all the group members were transported. And this is telling us we can continue to filter down our data, and we still have a lot of data to work with, or it seems like we have a lot of data to work with, and we can dig into why are these clusters or communities of passengers all being transported to another dimension when in aggregate only half the passengers were transported. I know we're getting a little bit close to time, so I am going to keep it moving. The next thing we need to do is we want to use some of the algorithms to algorithmically analyze our data. And what we'll need to do is project a homogeneous graph. And in this case, we're going to focus on surnames and groups. And so what we're going to do is we're going to have a graph of just surnames, and the relationships between them are going to be where the surname is in the same group. And so the relationship will be the group, and the node will just be the surnames. We're using a cipher projection here. That's a whole different subject. I'm not going to spend a lot of time on it here, but we're going to start using algorithms to calculate what can we learn from this homogeneous graph. And in this case, we're going to calculate a weighted degree centrality because the count, the property on the relationship is the number of groups that the surname shares. And so if we run gds.degree.stats, that'll, we can generate statistics, and we can see that we have a big spread in our data with the lowest value of 1 and the highest value of 26, or actually 32 here. So we'll take that, we'll write it back to our graph, and then we'll run some cipher queries to see which of our surnames, when you're looking at just surname and common group, what are the surnames that are the most connected or have the heaviest relationships in the data. And we can see right here that we have a couple of surnames that really seem to stand out as tightly connected or important within this homogeneous projection of surnames and groups. I'm going to skip this code. This was just going to pull out those three surnames. We'll be taking a look at it a little bit more in 1 second. The next thing I want to get to is weakly connected components. This is another algorithm that when you're performing exploratory data analysis on a graph is really something you should work with. It's something that we recommend you use early on when you're exploring a graph. Once you generate a homogeneous projection, what it's going to find are different clusters or communities of members or of elements in the graph that are tightly connected within the overall graph. And it will help identify, like, what are these components that are connected to each other, help you identify communities where you want to explore a little bit further. And so we will call this, and we'll see that we get a spread of, how many surnames are in each component. These are the statistics we're looking at here, where on average we have almost 2.5 surnames per component, but we have some components with 5 different surnames, and those would be the ones that are really tightly connected, and we want to explore that. So we'll run weakly connected components, write it back to our nodes, and then look for, okay, what are the components that have 5 surnames? And we can see here we have 6 components, each of which have 5 surnames. And if you want to go ahead and view those, we can actually run a Cypher query, match on the pattern, and then pull back, because we wrote the component number back to the node, to the surname node, we can filter for those using Cypher and view them in the browser. And that's what I'm going to do right here. And you can see, using a very similar pattern that we were matching on before, we have we have a lot of connections here. I will zoom in, and what I want to emphasize or show is that, let's see, here we go. I just want to separate these out a little bit and show you that within each cluster of nodes, I just want to separate this one a little bit more. So we're going to focus on just this one right here. And the colors might not be coming through, but you can see in this cluster, we have 1, 2, 3, 4, 5. 5 surnames in each of these clusters in the graph. And we're almost at as many nodes as you would want to see in a visualization. But each of these clusters has these connected components, these weakly connected components. And we can look at what are the surnames connected to passengers, connected to groups, and see how are they connected and what's common among them. We're not filtering on group size or percent transported, but we're just seeing that these are natural clusters that the algorithm is bringing back to us in our data. Now, the last thing that we're going to run is going to be a weighted PageRank. We're also going to see, PageRank, that's the algorithm that made Google. And we want to see which of the surnames are important based on being connected to other surnames in the graph projection. And so we'll run it and we'll write it back to the nodes. And we can see, again, another pretty good spread in the data, where the max has a 1.8 and the minimum is a 0.4. So there's some distribution we can work with. And we can go ahead and query. We can run a Cypher query. All this code is in the notebooks. And we can see which of these surnames are most important compared to, or based on being connected to other high-ranking or highly important surnames in our database. And we can see there's a handful here, especially these 3 at the top, that appear to be the most important based on their connections to other surnames. And just like before, we can go ahead and match on that and view them, in the Neo4j browser. And each of these you can see is connected. They're not connected to each other. They are distinct communities, but if we start expanding out the nodes, there's a very good chance we could find connections among them. And that actually brings us to the end of the notebook demo. I know we're very close to time. Just a few other points to wrap up, and then we can be on our way. I showed this slide at the beginning of the presentation, and I want to revisit it. The entire idea here, even though we were working in notebooks with a lot of code and Cypher and Python, the key concepts are what was most important here. And what I hope everyone can take away is leverage what you've learned before. Leverage what you learned when you were becoming a data analyst or a data scientist, and build upon what works. When we're working with graph data, there's a lot of things that we learn from tabular data that apply. Focusing on the business question. Do we have enough data? Is the data complete? Is the data high quality? Are we visualizing our data? How are we processing and creating new features? And how are we using a lot of the common, the really tried and true tools, whether it's Python, SQL, or other applications, to build and format and process this data? But whether you're working with graph data or if you're converting tabular into any different type of data, but especially graph like we were talking about here, adapt where necessary. Do you have a graph-shaped problem? Have you done sufficient EDA to inform a graph data model? Are you doing pre-processing and feature engineering in preparation for generating a graph data? Instead of thinking in rows and columns, are you thinking in nodes and relationships? Are you visualizing graph patterns and then generating graph-based features? I know we had to move really quickly towards the end there, but weakly connected components, page rank, there's a lot between this, all different centrality measures. There's a lot of graph-specific features that you can generate once your data is in graph. These are very informative, and you can use them either on their own or feed them back to a machine learning model, to help improve your accuracy or performance. And so now it's your turn. Now it's your turn. And what I hope you can think about is, first and foremost, how do you adapt your workflow to incorporate EDA and specifically graph EDA? Are you even doing it? Or it's not something that's really been explored. And so I hope the code and some of the techniques will give you ideas for things that you can adapt or build upon in your common workflow. If you have any feedback or you see issues with the code in the notebooks, by all means, please let us know. I mentioned before, we didn't really have time for questions, but we will do everything we can to address them in the Discord or elsewhere. I'll work with Alexander and the team. And finally, if you're new to graph data science, if you're new to Neo4j, check out Graph Academy, check out all the great webinars that we produce, and especially check out Nodes, the Nodes lineup in 2 weeks. I know I'll be there. I'm looking forward to it. And I hope everyone else will join us as well. And with that, I want to thank you so much for attending. This was a great experience. I'm really glad we were able to share this webinar. I hope you found it useful, and I wish you the best of luck with your projects.
Cool. Thank you very much, Dan. That was great. That was very well run presentation and slides. So that was really, really good and really interesting. Lots of positive feedback already in chat right from the get-go.
Thank you so much.
Lots of people seem to liked it as well as I did, and other people. So it was really helpful, I think, for lots of people to understand the process, the thought process that goes into it, and then you go from taking your tabular data and making it into a graph. So I think that is a very important step, a very important process that has to happen, and it's particularly interesting about the data set. I'm now almost feeling like part of this mystery thriller a little bit. So I want to know what's what's going on. But that was obviously maybe not only a side note for the data model, but it's good to see. There was one particular question I'd like to address before we close it. In your notebook, especially in the beginning, there is this segment where you load the data, and there is what's it called? This segment where it's connect to Colab, it says, and it connects to a My Drive location. Is it? Did you just take the Kaggle data set and people can download that from there, or did you do some data adjustment on the
That's an excellent question. I should have mentioned it before. I started with the data as is from Kaggle. And so if you want the underlying data, Kaggle gives a license where you can use this data. It's a Kaggle data set. You can use it for any purpose. I didn't save the data set on the GitHub, but the data is free and available. If you have it, in this case, I was working with Colab, but if you're just working on your machine or on a different platform, you can even just analyze the data as is on Kaggle. If you open up the notebook in Colab, you can actually just bring the data in directly. But the easiest thing to do would be to go to kaggle.com and just search for Spaceship Titanic. The data is right there and it's easy to download. You could even run this notebook on Kaggle, and all you'll have to do is change the pointer or the directory of where it's pointing to in the data, whether you're working on a machine or a different platform or on Colab. And so that should be, I hope it's straightforward. If there's any questions about that, please let me know. But the best bet would be just download the data directly from Colab, or I'm sorry, from Kaggle, and just change that pointer. If you're not using Colab, you can just delete those cells. But that's just how I did it. And it should be easy. Even from GitHub, if you go GitHub to Colab, or there's a button right there. If you have a Google account, it's easy to open up these notebooks in your own Colab. And you just have to save the data into your directory there.
Yeah. All right. That's cool. So I linked the Kaggle the data set in chat. Sometimes it will be down in the YouTube video description. So if you watch this on YouTube, check out the links alongside the YouTube video there. I collected them all, the important ones. So the Kaggle link to the Kaggle dataset is there as well. I mean, we could go on with some questions, but as Dan said, take it to our community forums, take it to Discord. We are there. We can discuss things further on these pages. So that's what they're meant for. Register for nodes again, that's another thing I'd like to weave in just before we close. And we do regular live streams on YouTube and other channels. So if you want to watch more, don't forget to subscribe to our YouTube channel so you get notifications. So for instance, tomorrow I'll have a special guest talking about data and art and the mix of these two forms. So we will make some art out of graphy data. So I think that's going to be a fascinating session. Again, Dan, thank you very much for taking the time to present today, for preparing this amazing workshop. Thank you all for watching. I hope I'll see you around either in another live stream or at Notes or somewhere else. So that's the main goal, to keep the conversation going. Otherwise, community forum or Discord is always open for more discussions and just lovely chat around the world of graphs. So that's what it is all about. And yeah, with that, I wish you all a great rest of your day, week, and speak to you soon.
Great. Thank you very much, everyone.
Everybody. Bye.